Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. And today we are going to discuss clamper circuits. So this is one of the important applications of diodes. So let us see overview of the today's session. So today we are going to discuss what is clamper circuit, the basic concept of clamper circuit, and types of clampers, positive clamper and negative clamper. So conclude with the summary. So let us see the first one, clamper circuit concept. So what do you mean by clamper? So the circuit that places either positive or negative peak of a signal at a desired DC level adds a DC component to the signal. So if you have a sinusoidal signal as an input, if that signal is applied to a clamper circuit, the clamper circuit used to shift vertically the input signal either positive or negative side. That means it shifts the analog AC signal to the positive side or negative side. Okay. So that means the circuit that places either positive or negative peak of a signal at a desired DC level. That means what? It adds some DC level for your input sinusoidal input signal or square signal, and no change in the shape of the signal. So this is very important point. See, when you compare this clamper with the clipper circuits, in clipper circuits the shape of the signal will be disturbed, whereas in this clamper circuit, the clamper circuit does not change the shape. Okay, and that means it does not change or alter the peak to peak value of the input signal. It just shifts vertically either positive side or negative side. So this is either positive side or negative side, vertical shift of the signal takes place. So that is the basic idea of clamper circuit, and it changes the peak and average value of the signal. Actually, if you see example for this clamper circuit, this is an example. So we have an input signal, sinusoidal signal. So this is a sinusoidal signal. What is the average value of this sinusoidal signal? So we have positive peak and negative peak. So if you take the average of these two, so this will be cancels out and the average value of this is 0. The average value of this given input signal is 0. And what about the peak to peak value? This is plus 5 and minus 5. So peak to peak value is 5 volts. So therefore, if you apply this kind of input signal, the clamper circuit changes the peak and average value of the signal, but it does not change the peak to peak or RMS value. The readings will be same for both input and clamped output. See, if you measure using an AC meter, voltmeter, the input reading at the input side and output side. So both having the same value. So that means even after shifting the signal, the peak to peak value does not change. Only it shifts from either positive side or negative side. So here this is a positive clamper. So what happened here? So the peak to peak value is plus 5 and minus 5. So total 10. So that means what? Peak to peak value does not change here. So only it adds this clamper, positive clamper adds some DC value to the AC signal. That means it shifts either upper side or lower side. So because it is a positive clamper, so your input shifts towards the positive side. So hence this is called positive clamper, and the average is also changes. Now if you take the average of this, so initially the average of this is 0. The average value of this input signal is 0, whereas if you take the output, clamped output, the average value is what? 10 plus 0 by 2, that is 5 volts. 10 plus 0 by 2. So that means the average value changed, and at the same time peak value changes. What is the peak value now? Plus 10 volts. Previously it is 5 volts. So this is the main motto or basic idea of clamper circuit. So let us see different analysis of this clamper circuit. See here, basic idea of a clamper circuit. The shape and peak to peak or RMS value should not be changed. So this is very, very important. So clamper circuit should not change its peak to peak value and or RMS value. It basically the basic components required to design any clamper circuit. So it consists of a capacitor, a diode and a load resistor. Now the operation of clamper, if you see, so this is the positive clamper. So this is positive clamper. So we have taken the example of positive clamper. So this is your, why it is positive, we will discuss one by one. So here negative is connected. So that means anode and cathode being negative. So this is a capacitor and diode and load resistor. See here, so basically it depends on the charging time and discharging time of the capacitor. See, it is based on the principle that charging time of a capacitor is made very small when compared to the discharging time. The charging time of the capacitor, so the moment you apply the input signal, the capacitor has to charge immediately. The charging time is very less. So we have to make the charging time must be less compared to the discharging time. Then now charging time, let us see the calculations of this charging time constant, that is when it is connected in forward bias. When this diode is connected in forward bias, the capacitor start charging. So that charging time is given by tau is equals to RFC, time constant. So capacitance and forward resistance of the diode. So here we have given forward resistance RF as 10 ohms and load resistor as 10 kilo ohms. And capacitance value is 1 microfarad. So therefore, based on these data, so we can calculate the time constant, that is charging time constant, tau is equal to C into RF, C or RF into C. So C, this is 1 microfarad capacitance, so 10 to the power minus 6 farad into forward resistance of the diode is 10 ohms. So if you multiply these two, the charging time is 10 microsecond. 10 microsecond means very small. So, and then the charging time of a capacitor. So usually we know from the electrical engineering, we can say that the charging time of a capacitor is given by tau C is equals to 5 into C into RF. So 5 times into C into RF. So that means 5 into 10, that is 10 microsecond. So here we got 10 microsecond is the time constant. So therefore we can write 50 microsecond is the time constant, charging time of the capacitor. And now discharging time of the time constant, let us see. So when it is diode is reverse bias, in such case we have a tau is equal to C into RL. So that is across this load resistor discharging time. So the capacitor discharges through RL. So therefore 10 power minus 6 F is the capacitance and RL is the 10 kilo ohm. So 10 into 10 cube. So you will get 10 millisecond. So when compare these two values, 10 microsecond and 10 millisecond. Okay. So 10 microsecond charging time is small. So the moment you apply input signal, so the capacitor charges up to the maximum value of the input, and the discharging time is 10 millisecond. So it is large compared to charging time. Okay. So it slowly, the capacitor slowly discharges because it represents 10 milliseconds discharging time, means it slowly decreases. Okay. So that means during negative, that is during reverse bias also, the voltage across the capacitor remains same. So therefore slowly discharging means in that time the diode output will be appear across the load resistor. So now let us see the types of clampers. So we have two types of clampers, positive clamper, negative clamper. and again positive clamper with positive reference, positive clamper with negative reference, and also negative clamper with positive reference and negative clamper with negative reference. So all these 4 types let us discuss. So input is assumed to be square wave. So here I have considered input as square wave. The clamped output is measured across the load resistor. So across this load resistor we will measure the V out. So the time constant must be large here. So we have made the time constant of the capacitor is large, that is voltage across the capacitor does not discharge significantly during the reverse bias also. So during the reverse bias the sudden discharge cannot be taken place in the during reverse bias also. So that means the voltage across the capacitor still remains same. So during reverse bias also. So therefore, so if you see the operation of this positive clamper circuit, so this is your capacitor and resistor. So how to remember this is positive clamper means, so this arrow indicates, so upwards, so like this, then it is positive clamper. So if it is downwards, the arrow downwards, that means arrow means what? Current flow, okay, of a diode. So then it is negative clamper. So this is the way of remembering the circuit: positive clamper, negative clamper. So let us see the operation of the positive clamper. So during negative half cycle, so this is negative half cycle of the diode gets forward bias, because this is minus and this is minus plus. So during negative half cycle means this one. So this is during negative half cycle means minus. So minus is connected to negative of the diode, that is cathode of the diode. So both are negative, hence it is forward bias. So what happens when it is forward bias? Diode is forward bias means it acts like a short circuit. It acts like a short circuit. That means what? Whatever the input voltage we have applied, so the total voltage will pass through the short circuit, that is through the diode. So nothing will appear across the load resistor. So entire voltage, input voltage is available through flowing through the diode only, across the diode, and nothing will appear across the load resistor, and V out will be 0. Okay, so that means does not conduct short circuited, small time constant, hence voltage is 0 across the load. And now during the positive cycle, that means during the positive cycle means this one, what happens? The positive and this is cathode. So if positive is connected, positive of the battery is connected to negative of the diode, then it is, say, we can say this is reverse bias. So reverse bias means it acts like a open circuit. It acts like a open circuit. So the output will be what? See here. So we have plus V volts and across the voltage V. So therefore we have 2 volts. That means plus V. That means if you apply KVL, Kirchhoff's voltage law, if you apply KVL, the total voltage is equals to V plus V minus. So because it is minus, so therefore V out is equal to 2 volts. That means what happens here? The voltage doubles here, peak voltage. So what happens? The peak voltage is increased. So previously it is V. Now due to this positive clamper circuit, the voltage has become 2 volts, doubles. What you observe here? The shape changes. The shape does not change. Only thing is the input signal is shifted towards positive side, and the peak to peak voltage increases 2 volts. Okay. So therefore this is about a positive clamper circuit. So now let us see another one, that is positive clamper with positive reference voltage. So here again, here next case I have assumed sine wave as the input. So previously it is square wave. We can also take square wave also. So for the simplicity I have chosen sine wave as an input. So if you apply this sine wave to the clamper circuit, so what happens with some reference? So we have applied some reference voltage. So it may be VR, this VR may be 1 volt, 2 volt, 3 volt. something like that. So it is positive reference. So positive reference. So this is anode and this is cathode of the diode. Okay. So now what happens here? This is the reference level. So whatever the reference we have applied, so this much of reference voltage will be added or shifted towards the positive side, because it is a positive clamper with some positive reference. So some positive voltage will be increased. So some positive reference voltage will be added to this actual input signal. So we can say this as Vm plus some Vr. Vm plus reference voltage. So it becomes 2Vm plus Vr. So this part will be Vm. Similarly, the same thing can be done with the negative reference. So this is the positive clamper with negative reference voltage. So again, I have assumed input as sine wave and the clamped output is measured across the load resistor RL. So in this case, what happens? Previously it is positive reference. Now in this case, we have applied negative reference voltage. So when you apply minus, this is minus and this is cathode. So therefore here this is your, what happens now? This becomes 2Vm minus Vr, because actually it is 2Vm. So this part will be Vr. So that means total will be 2Vm minus Vr. Peak value will be, the peak value has been changed because with this reference, negative reference voltage. Okay. So this is the way to represent a positive clamper with negative reference voltage. Similarly, next one is negative clamper circuit. So input is assumed to be square wave now and the clamped output is measured across the load resistor RL. So in this, during positive half cycle, what happens? During positive half cycle, the diode, see here, the diode gets forward bias, because here in this case the diode is reversed. So anode is connected to positive of the input. So therefore, hence during positive half cycle, the diode gets forward bias and it acts like a short circuit. So it acts like a short circuit. So whatever the input we have given, that will be across the diode. Through diode it will ground it, and then there will be no voltage across the load resistor. V out is equals to 0 here. And then similarly during negative half cycle, so because we have considered that the charging time constant of the capacitor is small, so we have made time constant, the charging time will be small and discharging time will be more. So that discharging time of the capacitor is very high, so that means it's slowly discharging. So that means during the positive cycle, what happens? The reverse bias, so here negative. So during negative half cycle, the diode gets reverse bias. So capacitor remains fully charged during non-conducting of the diode. What happened here? So during reverse bias, even it is reverse, but diode is reverse bias. So reverse bias means open circuited. So capacitor slowly discharging because the discharging time is more. So that means the capacitor remains fully charged even your diode is not conducting. So that's why you will get the peak voltage. So therefore here in this case negative side, negative clamper means the output, the input will be shifted negative side, that is vertically to the negative side. So the total output will be, if you apply KCL, so minus V and V out, minus V out. So minus V and minus V out gives you 0 volts. And V out means what? V out is equals to minus 2 volts. So that means the peak voltage increases negative side. So this one. Okay. I hope you understand this concept, negative. Similarly, negative clamper circuit also can be analyzed with different applying different reference voltages. See here, a negative clamper with positive reference voltage. That means what? We have added some positive to the negative clamper, positive reference voltage to the negative clamper. So during this time, what happens? So some voltage, VR voltage is added. The reference voltage VR is added to the negative. So hence it is some portion is in the positive side, even though it is negative clamper. So we have applied positive reference voltage, so that will be added to the output. So that reference voltage is present in the output, positive side. Similarly, the next one is negative clamper with negative reference voltage. So here input is sinusoidal signal again, and if you apply this reference input signal to a negative clamper circuit with some negative reference. So negative reference means it adds means this negative side will be added. So this will be your VR. So this part will be VR, and this much, and here you can say V 2Vm minus 2Vm, you can say, because you will get minus V plus, and we have added minus VR. So minus 2V and minus VR. So will be the minus 2V and minus VR will be the output. So this is about a negative clamper with negative reference voltage. So we can analyze in such a way that, and we have to choose the values of capacitor and RL, load resistor, in such a way that the capacitor must be discharged slowly. So the discharging time of the capacitor must be high compared to the charging time. So charging time, so the moment you apply the input signal, the capacitor must charge immediately, and during negative half cycle, the capacitor must discharge slowly. And then during reverse bias also, since the voltage across the capacitor remains same, then the voltage available across the output. So that's why, the applications of clamper circuits are very in the industry are there. So let us see the applications of clampers. So this type clampers are used as direct current restorers. Direct current restorers. So means DC restorer. So if you know, this is DC restorer. So in some applications, specific applications in digital circuits, some DC restorers circuits required. In such case, so combination of capacitor and diodes are used. In such way, DC restorers are very useful, and it is also used to remove distortions. What do you mean by distortion? Distortion means unwanted ripples. Unwanted ripples, that means undesirable content, AC content in any particular DC electronic device. So that can be divided, because what is the basic function of your clamper is, it does not change the shape of the signal, input signal. It just shifts, or it adds DC to the AC signal. And it can also be used as voltage multipliers. So when you want to multiply, so different voltages. So when you connect in series, so we can able to multiply the voltages. So in such case, voltage multipliers are there. For the protection of amplifiers, so we can protect the amplifiers using clamper circuits, and we can also use this clamper circuit in test equipments, laboratories. Okay. And then we can also use in baseline stabilizers. Stabilizers means power supplies. So DC power supplies, like that. Okay. So that's all about for today's class. So what we have discussed today, summary of today's session. So we have discussed the clamper circuit concept and types of clampers: positive clamper, negative clamper, and then positive clamper with different reference voltages, positive reference voltage, negative reference voltage. Okay. So, and their applications we have discussed. Now The next topic will be Unit 3, that is BJT, bipolar junction transistor. So it is the advancement of the diode. So we'll discuss in the next session. Thank you.